Okay, so in this video, we're going to talk about universal law of gravitation. Up until now, we've only really dealt with gravity as far as what the gravitational force is of Earth pulling on you or your weight. But it turns out that all objects with mass can cause a gravitational force. So let's go ahead and define what universal law of gravitation is, and then we'll look at some examples. So all objects with mass have a gravitational force, okay? And it's a non-contact force, which means that the objects don't have to touch in order to apply a force. And if you think about like a magnet, for example, if you bring magnets really close to each other, they can either attract or repel depending on which poles you're bringing close to each other. But if you notice, if you bring two similar poles together, let's say a north and a north, it gets really tough to push them together the closer you get, right? It's not like the force is constant. The closer the two poles are to each other, the closer you bring them together, the stronger the force is of those two poles repelling each other. And gravity behaves very similar, but the main difference is that gravitational forces only attract. There's no such thing as anti-gravity. And so let's just go ahead and define with an equation what the universal law of gravitation looks like. So let's say we have two objects. We're going to say object 1 has mass m1, and we'll say object 2 has mass m2, and we'll just say that they are some distance apart, and this distance is between their center of masses. Okay, so for two objects some distance r apart with mass m1 and m2, they will feel a gravitational force acting on each other. So there's a gravitational force of F2 on 1, and then there is a gravitational force of F1 on 2. And we know from Newton's third law that those two forces are equal. F2 on 1 is equal to F1 on 2. And so, for example, whatever weight that the Earth is pulling on you with, so if you weigh 150 pounds, for example, that means that you are also pulling up on the Earth with the same force of 150 newtons. Okay, so the Earth is obviously orbiting the sun. Whatever force that the sun is applying on Earth, the Earth is pulling back on the sun with that same force. So this force between them, gravitational force, we'll call it F big G, is equal to big G mass 1 times mass 2 divided by r squared. Okay, this equation is in your equation sheet, so you don't have to remember it, but we should use it often enough to where you will remember it. So as we talked about, m1 and m2 are mass of each object. R is the distance between the center of mass of each object. And then big G is a universal constant, and it is equal to 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. And so this number is a constant everywhere in the universe. It doesn't change. That equation is also on the formula sheet, so no need to memorize that. And so what you notice with universal law of gravitation is that the force due to gravity between two objects is proportional to their mass, and it's inversely proportional to distance squared. So as you bring two planets, for example, closer, the force due to gravity between them is increasing exponentially. And then if you take them further away, then the force due to gravity decreases exponentially, which is why if we travel, let's say, to the moon, the force due to gravity from the Earth acting on us is decreasing exponentially. You start to feel more force from the moon than you would the Earth. And so let's go ahead and look at an example. And first example we're going to look at is we are going to look at how the Earth is going to affect the moon with a gravitational force. Okay, so a couple of things that we want to find. We want to find the force due to gravity of the Earth pulling on the moon. We want to find the acceleration of the moon as it orbits Earth, assuming we're going to assume that it is orbiting Earth in a perfect circle, circular orbit. We will find how fast the moon is traveling, v, and then we want to find the orbital period of the moon, which is the time it takes to make one orbit around the Earth. Okay, so find all of those for the moon orbiting Earth. Okay, so here's a picture of what that looks like. Here is the Earth, ME for Earth, and then we've got the moon. Just draw a dot for the moon, has mass m, and it is going to be orbiting in a perfect circle. Not really a perfect circle, but you get the idea. Okay, we are interested in how far away the Earth is from the moon. Call that little r. And so let's go ahead and I just looked up these values on the internet, and the mass of the moon is equal to 7.35 times 10 to the 22 kilogram. The mass of Earth is 5.97 times 10 to the 24 kilogram. And then we have the distance between the Earth and the moon is, we're going to assume it's 3.8 times 10 to the 8 meter. All right, so first thing to do is find that force due to gravity. So force due to gravity is equal to big G times mass 1 times mass 2 over r squared. Okay, in this case the two masses would be the mass of the Earth and the mass of the moon, so we'll just plug those in. We have for big G, it's 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. And then we're going to times that by the mass of each object. So 7.35 times 10 to the 22. And then, so that was for the moon, and then the Earth's mass is 5.97 times 10 to the 24. And then we're going to divide all of that by distance squared. So it'll be 3.8 times 10 to the 8 meter, square that. So go ahead and type this in our calculator. Let's see what we get. So I'm getting 2, force due to gravity is 2.03, we'll just go with 2, times 10 to the 20 Newton. So really large force, that's 20 zeros after the 2, which is to be expected because these are really large objects. Okay, so we found force due to gravity. Next thing we want to do is find the acceleration. So a couple of ways to do that. We're going to do the easiest way and just do acceleration of the moon using Newton's second law should just be the force acting on the moon, which is what we just found, divided by the mass of the moon. So we'll go ahead and do that. 2 times 10 to the 20 Newton and divide that by mass of the moon is 7.35 times 10 to the 22 kilogram. Okay, so we end up with, put this in our calculator, 7.35 second. Okay, end up with an acceleration of 0.003 meter per second squared. I'm going to do that one more time just to make sure. All right, so 0.003 meter per second squared. All right, so not very much. We said assume this is a perfect circle, so this is the centripetal acceleration. And so knowing that, we can get how fast the moon is moving. So the next thing to do is find velocity, and we're going to use acceleration centripetal is v squared over r. And then if I solve for velocity, that's going to be equal to the acceleration times r, and then we square root everything. So that'll be equal to 0.003 meter per second squared. Then we're going to times that by the distance, which is 3.8 times 10 to the 8 meter. Square root all of that. See what we get here. So 0.003 times that by 3.8. And we end up with a velocity of 1,060, we'll go with 1,068 meter per second. Okay, so last thing to do is find the orbital period. So it takes about 27 days for the moon to orbit the Earth, and so we're going to hope to find something similar to that. So let's see what we get. So to find orbital period, remember we're assuming this is a perfect circle, and so we can use the velocity we just found and set that equal to, we'll just say average velocity is some distance over time. Okay, the distance traveled by the moon, if it's a perfect circle, would be equal to 2 pi r, the circumference of its orbital path, and then divide that by the orbital period. And so if I solve for orbital period, we're going to get 2 pi r over v. And let's go ahead and plug in some numbers and see what we get here. So that's 2 pi times 3.8 times 10 to the 8 meter. And then we're going to divide that by the velocity we just found. So 1,068 meter per second. And if I do that, we're going to get a big number, so convert that to scientific. I'm getting 2.2 times 10 to the 6 second. All right, and so let's go ahead and convert this to days just to see how close it is to 27 days. So we have 2.2 times 10 to the 6 seconds, and we want to get that to days. So for every 3,600 seconds, that's going to be 1 hour. So the seconds cancel. And then for every 24 hour, that's going to be 1 day. And so we're going to take our number that we just found, divide it by 3,600 times 24. Okay, so if I do that, I'm getting 25.9 days, or we'll just say 26 days. So we were off just by 1 day. Okay, so we did assume that this was a perfect, a circular orbit, and eventually we'll talk about why planetary motion is not circular. So that's it for this video. Look out for more videos for more examples.